Last year, the Dark Energy Spectroscopic Instrument, DESI, made headlines around the world. Its enormous map of the universe hinted that dark energy, the mysterious entity causing the expansion of the universe to accelerate, might not actually be constant. More recently, another giant cosmology experiment released its final results, the Dark Energy Survey, DESI. Its results are intriguing, but did DESI confirm DESI? To answer that, we have to address a much more interesting question. Why are completely different scientific studies so much more powerful in combination than any single study on its own? The answer brings us to the heart of what science really is: eliminating hypothetical universes. Did DES confirm DESI? It seems like a reasonable question. New data is supposed to reduce the uncertainty on whatever number we are trying to measure. You tighten the error bars and you confirm the measurement. Science sometimes works that way, like when we first measured the existence of dark energy in the first place. But modern cosmology has reached the point where this approach no longer works. The signals we are looking for are so subtle and tangled together that it is no longer about directly measuring the parameters of this universe. It is about ruling out countless hypothetical universes that we are not in. And DES was ruthless in eliminating universes. Despite their nearly identical names, the Dark Energy Survey, DES, and the Dark Energy Spectroscopic Instrument, DESI, were built to tackle the same grand mystery from almost opposite directions. DESI's mission is beautifully focused. It measures the distances to tens of millions of galaxies, constructing the most detailed, three-dimensional map of the universe ever made. Hidden within this vast cosmic atlas is a faint fossil pattern left behind by sound waves that rippled through the hot plasma of the infant universe nearly 14 billion years ago. These are the baryon acoustic oscillations, BAO. BAOs give us a cosmic ruler that grows with the expanding universe, allowing DESI to trace the history of that expansion with extraordinary precision. DES took a much broader approach. This international collaboration of roughly 400 scientists took control of the Blanco 4-meter telescope at the Cerro Tololo Inter-American Observatory in the Chilean Andes. After building a dedicated 570-megapixel camera, they scanned an enormous region of the southern sky for 6 years, building an extraordinarily deep portrait and movie of 300 million galaxies. This became the foundation for several completely different ways of probing the cosmos. Weak gravitational lensing DES measures tiny distortions in distant galaxy shapes caused by the subtle Oort curve warping of intervening space by massive objects. Through this, DES maps the invisible distribution of dark matter and tracks how cosmic structure has grown over time. Galaxy clustering. It measures how galaxies have clustered together over cosmic time due to their mutual gravity, giving a completely different perspective on structure growth. Galaxy lensing. By combining lensing and clustering measurements, DES connects visible galaxies to the much larger halos of dark matter that surround them. Type 1a supernovae. DES discovered and monitored thousands of Type 1a supernovae, measuring the expansion history of the universe by determining distances to these exploding white dwarf stars, the method by which dark energy was first discovered. Baryon acoustic oscillations DES even measures the same ancient BAO pattern as DESI, but with a completely different observing strategy.